So this is another expanding and simplifying, but this is more complex. There's quite a bit more going on here. It's actually good. It covers quite a bit of all the things you may need to know. So we could take a look at the very first set. When you have what's called a polynomial, we usually actually describe terms as being separated by addition and subtraction signs. So if we take a larger view, I could use even a let statement to make this look a little simpler for me. I'm going to do it just to show us, and then we're going to go right back to it because it doesn't help with our simplifying, but it does give us a little bit of a bird's eye view. I'm going to say let x plus 2 equal a, and let 3x minus b. And then the reason we're going to do that is just so we can take a look at how many terms we have. This is a 5a, and this is minus b squared. Now when we look at this subtraction sign separates. We have essentially two terms. One of them has an exponent to it, okay? This gives us a bird's eye view of what do we need to deal with. And if we think of our bed mass, technically I should deal with the exponent. Now in the version we have with our let statement, there's nothing I can do with that. But when I plug everything back in, so I'm going to do it again, I'm going to say let x plus 2 equal a again. This is just to communicate to the reader that we're redoing that process. We're going to go right back to the beginning, but the idea was that hopefully this gives us a better view of what we need to work with. We have 5 times a, and a happens to be x plus 2. So because these two things are being multiplied, this is that distributive property. And then we have subtract b squared, but b happens to be 3x minus 1. Well, 3x minus 1 squared, we can expand, okay? So I'll distribute, but in the next line, I'm also going to expand this into two sets of brackets. So when we distribute the 5 times x becomes 5x, 5 times 2 becomes 10. That's nice. We'll leave the negative here. The brackets have disappeared because we've already distributed on the first term. The second set, though, is two sets of brackets that need to be distributed by each other. Think of foil, rainbow, whatever it is, okay? So if let's say we do rainbow, we got to do this. Multiply the first term by both, and then multiply the second term by both. These terms are all going to stay the same. So I still have 5x, I still have positive 10, and I still have subtracted by, I'm going to leave it in a set of brackets because that negative needs to actually be distributed after. 3x times 3x is going to give us 9x squared. 3x times negative 1 will give me negative 3x. Negative 1 times 3x will give me negative 3x. And negative 1 times negative 1 is positive 1. So I've kind of sped through that one piece. I'm going to simplify the brackets before I distribute this negative. It'll just make the distribution a little easier. 5x plus 10 stays the same. We still have a negative. There's no like terms for the x squared, but the negative 3x and the negative 3x can be simplified to a single term, to negative 6x. We take negative 3 and subtract negative 3 to get negative 6x. And then we have that plus 1. Now we can go through that idea of distributing a negative, okay? Jump down a few lines just because of those arcs we got there. This becomes negative 9x squared. This becomes positive 6x, and this becomes negative 1. All of those negatives flipping, all the terms flipping becomes actually really important. So if we miss that step, we end up in a very, very different place, okay? Finally, we collect our like terms. So I have a 5x and a 6x. That'll be a set of like terms. I only have one x squared, and I do have two constants, 10 and a negative 1. So the negative x squared, when we write a polynomial, we usually write to the degree, variable with the highest degree first. It's not wrong to do it another way, but this is just common. When you're writing it out in mathematics, it's common to write it out this way. So negative 9x squared. 5x plus 6x will give us our 11x, and 10 minus 1 gives us our 9. But there's quite a bit of expansion we had to go through before we could simplify into 3 terms. In fact, take a look at how difficult this part looked to how simple our final answer is. So there's quite a few more terms in the middle there than what we actually ended up in the end with. I'm going to give you a real world example of this, where we get a scenario like this, and then they ask us to find the area, and where we have some knowns. Now, this is a weird known to have, 2x plus 10. But essentially to find area, I got to multiply lengths and widths. But this is what they call a composite shape. It has multiple shapes as part of it. We could split this. I could split it this way and have two rectangles, or I could split it across. I'll give it another redraw real quick. I could split it without writing down the actual parts. Oops, that wasn't great. I could split it like this. Both will give me the area. It's just I'm going to end up with different equations depending on how I solve this. Okay. In the first one, we will use. This one gets a little complex if we do it this way. It actually much easier. I'm going to tell you right now, after a very quick view of it, this version is much easier to work with. Okay. And I'll explain why. I'll write these in here and we'll set it up, and then I'll briefly talk about why this became more complex. This measurement is an x, so we literally have the two measurements. You can call this your length and this your width if you like. And then we have 6 and we have 2x plus 10. Same idea, and we have a width and a length. Those are really simple. To find the areas, we multiply both those together, and then we're going to have to add. This version, I don't have this distance. Oh, sorry, I lied. I have this distance. I don't have this distance. So I have to do some addition. I got to figure out that this becomes 6 plus x. Okay, not bad. I did get that piece. This is 6, but I don't have this distance. This distance is actually all of this subtracted by this, which is a whole nother equation. It ends up like this: 2x plus 10 subtract x plus 2, which I have to do a whole bunch of work. There's not too many extra steps, but this one was clearly a little easier to set up. Okay, so we'll work with this one. We have our first rectangle here. We're doing length times width, so we'll call this area of 1 and area of 2. So area of 1 is equal to length times width. We know that for area. And we've already defined them. Our width was the letter x, and our length was x plus 2. So we have x plus 2 times x. That one's not bad. And then we have area 2, which is also length times width. Our length was 2x plus 10. Ooh, pardon me. And then our width happened to be 6. These aren't bad. This is actually just distributive property. I don't even have to use that FOIL or rainbow method because I only have one term to distribute on both of these. This x needs to be multiplied by both of those, and this 6 needs to be multiplied by both of those. When we do it, we get x squared plus 2x, and we get, we get 12x plus 60. Great. Those are the areas that represent here, but to get the full area, I have to add those two together. So the very last step here is we'll call it total area, or I'll go area of t, is equal to area of 1 plus area of 2. And we're just going to substitute what we have for those. Area of 1 is that piece there, which is x squared plus 2x, okay? And then area of 2 is what we have over here, 12x plus 60. Because this is a positive, when you distribute, nothing changes. So we can just drop the brackets. This ends up just being x squared plus 2x plus 12x plus 60.
And then you group them together.
That's it. We group them together. 14x plus 60. That is the relationship, okay? Because we don't technically know x. Maybe in the question they'll tell you after that x is equal to 2. And then in the end, you can just plug 2 in and get a formula for this at the very end of it, okay? But that's the process for a question like that where you have a composite shape made up of multiple shapes.